All right, well, welcome to week 4 of vibrations, and we're going to cover the log decrement and Coulomb damping in this class, or in these classes for this week. Here's the basic idea, is we're going to use an empirical way to determine what the damping coefficient is going to be. So that's like the big idea in the log decrement. We can see what the decay is going to be by taking the peaks and seeing the relative position. So we will use the symbol lowercase delta, aka del, for this. I recognize that I will often use that to talk about a small displacement in perhaps like a spring or something like that. So sorry for double dipping with the letters, or the Greek letters. So here's the big equation for us. We will take the natural log of the, I'll call it a max 1, right? So that right there is x max 1 divided by x max 2. Pretty simple, really. That's the main equation for this log decrement. The other idea of it is that we have e to the del is going to be equal to that ratio of max 1, right? So we just took the natural log of it. And this is going to be a larger number right here than this one. I didn't finish writing that down. So basically what we want to try to do is we want to find if we have a formula for this as a function of time. We could say we have some big magnitude, this maximum magnitude right here, boom, times e to the minus, and we'll use this form of this where we have the natural log times t, and then this is times the sine of the damping natural frequency, the damped natural frequency right there. So that is the equation for this line right there, right? So what we're really trying to do is sort of find what that is. Well, our main goal is to find actually this right there. So we want to find this, is what our goal is from up here. So the equation that we might want to put up into there is, and this is for, by the way, this is for a period, right? Because it's between peak and peak, so it's going to be a damped period. So we will also say that that log decrement is going to be my damping factor times my undamped natural frequency times my period right here, right? So here is another formula that we can use for the point of this thing. So we also know, let's see, we'll right over here. So this is something we can also know that from our damped, this is just a formula. We could say that this right here is going to be equal to, the period is going to be equal to 2 pi over the natural frequency times the square root of 1 minus this. All right, so this right here comes from, we're basically just saying that the damped natural frequency is going to be equal to omega n times the 1 minus the damping factor squared, right? So that's like, let's see, let's go little thought cloud. Little thought cloud. It doesn't like getting written on down in this corner. Right there, right? So from this, we get that. And so another thing we can write in here in using this is that del is equal to 2 pi damping factor divided by 1 minus the square root of 1 minus the damping factor squared. So this is also a useful equation that just comes from replacing tau the damped period tau d in with the definition of it. And then another useful equation could be this backwards, right? So we can, and you could just take my word for it, or you could try to do the algebra yourself. That we go, if we have del, we can find the damping factor by doing a little bit of algebra and go 2 pi squared plus del squared, right? So there's a bunch of equations right here, but they're all stuff that we already know. The only addition that we really did was this equation right here at the top. So notably, this, let's see, we can make a connection to this graph over to the side. That this equation right there is this equation right here. So you can see, here's your damping factor. And as it gets up to 1, it starts to approach 1, you could see that the log decrement starts increasing. We could also note that like right around in this vicinity and downwards, it becomes sort of a straight line, right? It becomes a linear type of thing. So you can see the thing on the denominator right over here, right over there, that starts getting closer and closer to 1. So what you're receiving is what you're having on the numerator becomes just a straight line relationship between the log decrement and the damping factor. All right, with a slope of like 2 pi, basically. Let's see. I don't know what my time is yet right here. And did I want to write anything else? No, I think I left a page right in there because I wasn't sure if I'd be able to squeeze everything in there. This is a good introduction, I think. The next I have is an example. So I am going to switch to a new video. And let's see if we can't get this thing to stop.